The goal today is to introduce you to the powerful filtering feature of the MX and PTX platforms. I'm David Rowe, Principal TME at Juniper HPE Networking. I'm presenting this video, but the content was developed in collaboration with my colleague and friend, Nicolas Février. Let's start with concrete customer use cases. We implement a filter with over 3,500 terms and more than 500,000 prefixes, or a filter with fewer terms but using a large number of unique prefix lists, more than 3,000 in this case, or even a very specific filter used, for instance, to offload firewall flow table on a router with more than 225,000 unique 5-tuple entries. These are just a few examples of customers using MX or PTX routing products, demonstrating the power of Juniper routing solutions in data plane filtering. Let's start with the basics. A filter, also known as an ACL, is a set of entries or terms that each combine a matching conditions under the from statement and a set of actions to execute if the conditions is met. The filter is then applied or attached to a specific interface, subinterface, or even a forwarding table in either the ingress or egress direction. In practices, a filter configuration is first optimized, compiled, and only then programmed into the hardware. On platforms like PTX and MX, a single filter can contain hundreds or even thousands of terms. Each term typically includes standard match criteria, the well-known 5-tuple, source destination IP, source destination port, and the protocol field. In red on this slide, we highlight the less common match types like TCP flags, packet length, or flexible match, which allows deep inspection into the payload. Also remember, each of these fields or match criteria can scale to very large values. Once a match is found, a corresponding list of actions that could be simple or complex is executed on the packet. A filter instance is often attached in a direction to a logical interface, as shown here. However, as mentioned earlier, we also support the forwarding table attachment point, which is very useful in certain cases and quite unique in terms of implementations. So when it comes to high scale and high speed filtering, flexibility, performance, and scale are the three primary challenges to address. Any implementations should pay attention to the ability to inspect various fields across different headers, including deep inspection into the packet payload, and going beyond simple permit or denied actions. For instance, being able to modify packets on the fly, change forwarding behavior, and apply advanced actions. An implementation should also support a very large prefix list, in some cases several thousand of unique prefixes. The ASIC must make filter execution as fast as possible, even when combining hundreds or thousands of terms. And finally, we need to ensure all this works within a finite system resources, especially the memory. One of the key solutions to address these challenges is our in-house technology built on years of experience. This secret sauce is called FLT, Fast Lookup Table, composed of several blocks. It is a filtering model specifically designed and optimized for both simple and highly complex use cases. FLT is implemented in both our Express and Trio ASICs and continues to benefit from ongoing innovations. On the left side, we show how the FLT block is integrated into the Express pipeline. Similarly, on the right side, we show its integration into the Trio ASIC. The FLT block combines multiple technical innovations, including custom compressions and search algorithms, making it one of the most scalable filtering solutions available on the market today. Before we dive into the details, here is a quick look at the history of FLT. In the early days of Trio, filtering was handled by the ASICs microcode. This is still the default method today, and it has also seen many improvements over time. The FLT block was originally designed for the Express ASIC family, and only starting with the third generation of Trio, we did begin to bring FLT concept into Trio as well. More recently, the FLT block has been enhanced on both Trio and Express. This allows us to support billions of operations per second on Express 5 and to handle very large and complex filters on Trio 6 without any performance degradation. Let's start by looking at the internal structure of the FLT block on Express. It is mainly made up of 6 functional blocks, 2 alpha blocks, 2 beta blocks, 1 TCAM block, and 1 special block called the cover vector. Each block has its own specialty and runs different search algorithms. For example, the 2 alpha blocks are optimized for IP address lookups, while the beta blocks are better suited for range-based matches, like port numbers. All these blocks operate in parallel to ensure fast and efficient execution. We now have one dedicated FLT block per data path with the latest generation of Express, the 5th generation. What is important to note is that on Express, the FLT block is highly optimized for performances. We support up to 5 billion of filter operations per second in the latest generation, and at the same time, it can also process up to 256 filter terms in parallel. On Trio, we offer 3 main solutions for filtering. The first one is the standard firewall filter, also known as the DMEM filter. The Trio ASICs fully manages in hardware this type of filter, and all entries reside in the DMEM memory. Filter execution is done sequentially, but offer massive scale. For example, up to 1 million of unique prefixes. For IP matching, we use a dedicated LPM structure called K3, which is the same structure used for packet forwarding lookup. DMEM filter match criteria offer a wide range of options, allowing matches against many packet fields as well as metadata associated with the packet, such as the forwarding class, the SCU or DCU tags. It also supports the except keyword for reverse matches, which can be extremely useful in specific scenarios. The second type of filter is known as 5-tuple filter. This is a relatively recent and unique feature introduced in release 24.2. This time, it relies on a large hash table rather than sequential processing. The filter is dedicated exclusively to IPv4 5-tuple matches and is designed for specific use cases such as DDoS mitigations or firewall flow table offloading. We covered these features in a recent tech post. I highly recommend checking it out if you haven't already. Finally, the third option is FLT. On Trio, the FLT block is like a filtering coprocessor engine, offloading the ASIC from complex matching tasks, specifically the form part of the filter terms. FLT on Trio is made of 1 alpha block and 2 beta blocks. It's slightly different from a hardware perspective and was specifically designed to handle very large and highly complex filters. Unlike FLT on Express, only the 5-tuple The 5 standard IP fields are handled by the Trio FLT. But keep in mind that FLT on Trio can work in conjunction with the ASICs DMEM. For example, we could consider hybrid FLT filters, which are filters with terms that combine 5 tuple matches with other criteria, such as packet length, DSCP field, or even DPI level matching, thanks to the flexible match feature. In this case, a first lookup based on the 5 tuple is accelerated by the FLT, and then, during a second pass, only the matching terms are further processed by the ASIC if additional criteria needs to be evaluated. It's worth mentioning that the upcoming Trio 7 will include 2 FLT blocks, further enhancing performance. Additionally, a recent software upgrade now supports filter with up to 8K terms. We don't program the same object in the same block. On Express, all match criteria, including the 5 tuple and extended fields, are handled directly by the FLT block. As mentioned earlier, some functional blocks like alpha are dedicated to fast IP lookup. In contrast, on Trio, the FLT block only processes the 5 tuple matches. Any additional match conditions are handled in the second phase by the ASIC microcode. So let's illustrate how FLT works on Trio. We are injecting traffic, and the packets are expected to match term 5 of our firewall filter. This is shown at the top right. When a packet is received, the microcode extracts the 5 tuple from the packet and dispatches the field to the corresponding FLT blocks for processing. This is where our secret sauce kicks in. Each functional block of the FLT processes up to 256 terms in parallel in one single clock cycle. Then, each functional block returns its result as a sequence of bits. A 1 indicates a match, and the bit position corresponds to the term index. The cover vector block then performs a bitwise AND across all these partial results to identify the final matching term. Finally, the FLT block scans the result produced by the cover vector block and picks the first bit set to 1. The position of that bit corresponds to the first term that matched all the criteria. This result is then returned to the ASIC microcode, which may perform a second phase of search if needed. We discuss about that later. For example, to check non-5 tuple match criteria. Finally, the corresponding actions are applied to the packets, and all of this happens at line rate. Before wrapping up, let's look at a real-world example that illustrates why the FLT solution is the most scalable and optimized on the market. We'll compare a Juniper MX304 on one side and an alternative solution that, like many in the industry, relies on a TCAM-based filtering approach. So let's assume we want to deploy a filter that includes 12 identical terms. Each term contains the following 2 prefix lists, one for source IP match, the other for destination IP match, each with 128 entries. Then we have only one protocol, TCP in our case, 3 destination ports, A, B, C, and one single source port, D. Now let's try to map this filter into the TCAM-based solution. TCAM relies on pre-computed keys, and the number of required entries grows rapidly based on number of combinations. Let's do the math together for our example. Each term would request nearly 49,000 TCAM entries. With 12 terms, the filter will consume approximately 590,000 TCAM entries. unfortunately, just above the total TCAM capacity. As a result, compilation will fail simply because the TCAM cannot accommodate this filter. And now, let's commit this filter as an FLT filter on the 306 of our MX304. Since our filter consists only of 5 tuple terms, nothing is stored in the DMEM. After committing, we can monitor FLT memory consumptions. That was easy peasy for our FLT. Thanks to our secret sauce, we are using only 1% of the alpha block and almost nothing in beta. This is just one simple example where Juniper clearly stands out as the best solutions. And there are many other use cases where this advantage becomes even more evident. To conclude, I would say that in this video, we have only covered about 10% of the filtering capabilities available on MX and PTX platforms. Filtering on Juniper devices is much more than just FLT. It's a comprehensive toolbox of advanced features and ongoing innovations. Some of them are listed here. In fact, with every new release, we introduce enhancements and new features to stay aligned with our customers' evolving needs. If there is a specific filtering topic or feature you would like us to dive deeper into, especially if we went over it too quickly today, feel free to reach out. We would be happy to create a dedicated video or a tech post based on your request. Thanks for watching and have a great day.